Okay, here we say. Shall I
Okay,
start, Michael?
I think we're ready. Let me get you in the top. There you are. Oh, there's.
Get into and I just
You're anyways, whatever. It'll be fine. All right, folks. So I'm gonna, I guess, I don't know if I'm still in charge here, but I'm happy to introduce Peter Pang. So Peter's gonna give a sort of joint seminar between the summer school and University of Potsdam, where he's visiting for the week. And so Peter is, I don't know if he won like the best thesis in Netherlands last year or something, but he won some award for his doing Bayesian inference of, a variety of transients. A number of folks in this room have worked with him extensively. He's an expert in Bayesian inference and, applying kind of multimodal inference to astronomical problems. These days, he's a postdoc back in the Netherlands. So yeah, he's visiting Tim Dietrich's group this week, who, some of you may know works on a variety of gravitational wave problems. And so we're super happy to have Peter to give kind of the pedagogical talk. And so the kind of the main notebook for today will be based on doing inference on kilonovae. And so he's the one who, wrote a lot of the code. All right, so big thanks, Peter. I don't know if you what of that you could hear, but yeah, we're glad to have you.
Thanks very much for the introduction as well. So let's get started. So today I'm going to talk about, as Michael said, about Bayesian inference, basics of it, a bit of tricks and so on, and also how it's related to NMMA. So it's like the one piece of software that we built, and we use it extensively to like kilonova analysis, geometric detection, and also multi-messenger effects. So today's talk will be a bit long, so therefore I'll give an outline. So first, we will jump into the Bayesian inference. In particular, we will talk about the two main branches of Bayesian inference application for parameter estimation and hypothesis testing. And then the later part, we'll also talk about the computation method that we are extensively using for Bayesian analysis, like how we do sampling, how we actually calculate the base vector, and so on. After which, we will talk a bit more about the NMMA, so the software that we built. What is it? What does it do? And also what examples, what kind of science we have been trying to do with this software. So first, why do we need to have this kind of talk, or why do we have to, why this skill is useful in the first place? So first, statistics in general, or like Bayesian statistics, is essential for answering physics question. Like if you have some data and you want to extract physics out of it, you need statistics. And also, like if you want to make a discovery, you also need to make use of this statistical method for you to actually know that, oh, how confident I am that there's actually, like, let's say, an exposure, or how confident that there's actually a gravitational waves detected back in 2015. And for us, we are actually using it to be a more specific case. For our case, we want to use it to unlock secret from neutron stars or astrophysical events. For instance, if we use multi-messenger astronomy, we could actually look into properties of supernuclear matter and neutron stars, or we can actually measure the Hubble constant to see how fast the universe is expanding. Or we can also look into nuclear synthesis to see how elements are created, like from kilonova, how they're distributed around a ejector, and so on. But of course, it's much more than what I'm showing here. So after all, this is the main problem that we try to answer a lot of time in science in general, not just physics, like the inference problem. So there are two sides. One side is a lot easier, one side is hard. So the easier question would be like, under hypothesis, what would be the observed data would be, or the predicted data to be? For instance, like if I say I have a dice and assume it's a fair dice. So what's the probability of getting a 1? I think anyone that is older than 6 will answer like 1/6. Nothing special, super simple. Or a bit harder, like if I have a Kilnover model and I have some parameters, let's say the ejector mass, what would be the resulting light curve? Of course, it will be harder, but still it's doable. We have models and we just plug in the number and we get the light curve of it. And this part, the so-called easier question, is mostly what we refer to. Why there's a red line around here? It's what we refer to it like a it's gone out. Refer to it like in the Bayesian statistic point of view is the likelihood. The a bit harder question is the other way around. We flip the answer, flip the question. So given the data, how likely a hypothesis is true? For instance, given I have a dice, I rolled it 100 times. And given all this outcome, how likely the dice is actually fair? And how confident I am that this is actually a fair or not a fair dice? This is a bit harder to answer. I think if you ask a 60 years old, I don't think he or she could answer this question. And for instance, we can flip also flip the other way around. Like given 2017 GFO, basically the Kilnover from 17. What would be the ejector mass for this Kilnover just by the observed data? And this type of question, that's what we call the posterior in the Bayesian setting. What's the number? Okay. So why Bayesian inference is very powerful, like why Bayes' theorem is very useful, because actually it relates the two things together. It relates the easier question, therefore the likelihood, with the harder question, the posterior, which without Bayes' theorem, I have no idea how to calculate, to be honest. And here, you see that there are a few very key elements for Bayesian statistics. These are the names that you'll be keep listening to if you look into Bayesian books or so on. Like the posterior, basically you see that like posterior in the context of parameter estimation is that the probability distribution or the probability mass function given the data and hypothesis was that for a parameter. And for likelihood, which I should use the cursor so everyone can see. And the likelihood is the other way around. It's given a hypothesis and the parameter, what's the distribution or what's the data actually look like. And the prior here is actually one thing that is setting very different Bayesian and frequentist statistics is that for Bayesian, you always have a prior. So the prior is that before I conduct this experiment or observe this data, what's the expected distribution or expected sort of likelihood for the parameter itself. And then at the end, you will see there's a probability of getting this data given a hypothesis, which is so-called evidence. But of course, in the context of parameter estimation, Bayesian evidence is basically useless. It's just a normalization constant. But in a few slides, you will see actually the Bayesian evidence is a very powerful tool for you to do hypothesis testing.
Can I ask?
Yeah, sure, yeah.
This beta vector is the data. Or
No, this one is the parameter.
at the front.
Yeah, B is the data.
Okay.
Yeah. So like data could be like the mass of binary neutron stars. The data is a gravitational wave string and so on. So here is a very schematic looking at what like a Bayes theorem actually look like in practice. Not fully in practice, but more efficiently. So for instance, like we have a prior, the blue curve on the parameter X. Then that's still a bit wider, we don't know what it is. And now we have a likelihood, which is just a reminder, likelihood is not a probability distribution function for the parameter, but for the data. So it does not need to be normalized in this space. That's why I also plot it in dashed line. Just a reminder. And like for this, in particular, let's say the likelihood actually is peaking around 0.5 with some width. And the idea of Bayes' theorem is that with a prior and with some observation with the likelihood, we basically update our belief on the parameter itself. So basically, we can think of it, we go from blue, and then now we have the observation orange, and now okay, and it's more likely to be the purple rather than the blue one. So actually, that's why also if you have multiple detection or multiple events, you can basically like stack this kind of label up one by one, then you can get a joint posterior with multiple events, multiple detections. So this will get a bit more math. So in a lot of cases, when we actually do like a Bayesian analysis for parameter estimation, actually people will ask like, oh, actually how much information you gain from this analysis? How much more is it there? Because there are a lot of, there could be cases like the posterior does not differ actually that much from the prior, but you want to have a way to quantify like how much more information is gained compared to these kind of distributions. One of the common use statistics that we use is the so-called KR divergence. As you see here, it is not symmetric, therefore it's the KR divergence of posterior given prior is different from the one prior given posterior. And for most cases, actually, we're using posterior given the prior because we're thinking about updating from prior to posterior. And in case the prior and the posterior is exactly the same, then the KR divergence will be 0. And in case, let's say the posterior distribution is a Dirac delta, somehow you have a very strong likelihood, it's a Dirac delta with just one single parameter point, while the prior is a usual Gaussian distribution or uniform distribution, then you can have the KR divergence all the way to infinity. So it's unbound, but this KR divergence will always be non-negative. And of course, this thing also has units. It depends on what kind of log you're using. If you use natural log, the result will be in nets. If you use spatial log, you'll be more familiar with people that using computer every day, basically everyone, bits. And actually, like in here, there's a table that will show like a bunch of KR divergence of, let's say, the radius of neutron star or the pressure at different density. And actually, it's a very practical use case because actually our referee asked us to calculate it in our paper. So this thing itself is very practical, and actually people are familiar with using it as a quantification. But of course, what if I do not want to like compare the posterior with the prior as like comparing with whether how much information I gain. But what if like I have the same experiment, but I want to test a bit different technique that I want to do the analysis, and at the end I have two posterior, and I want to compare how similar are they. And one way of doing it would be using the so-called JS divergence. What it does is just symmetrizing the KR divergence. And then with this parameter, we can tell how different are two distributions. Like if they are exactly the same, it will be 0. If it's completely different, like because this value itself is bounded, it will be bounded at log 2. But again, the log will be the logarithm that you use for this calculation. If you use base 2, then it's very easy to visualize 0 and 1. That's it. But of course, all I just talked about is just the parameter estimation. What about the other part, the hypothesis testing? So for hypothesis testing, again, we will look into the Bayes rule or Bayes theorem, but now already a bit different. So you see now all the statements are gone, but instead I just look into the hypothesis of interest. Like for instance, I can still see basically just flip the sign of the hypothesis, the data of the we flip the sign of the hypothesis and data to here, become the posterior, but this is likelihood, prior evidence, and so on. But now you can see that it's a bit different. Rather than saying that, okay, now it's saying what is the distribution of a parameter or so on, we're actually quantifying how likely a hypothesis is true given a data. And one way of actually comparing would be, rather than calculating all this, actually we can put two different hypotheses like against each other, and then put them together. We'll have the so-called odds ratio. This one here, the odds ratio, basically quantifying like different data, how plausible one hypothesis is more likely to be true compared to hypothesis 2. The Bayes factor, Therefore, they flip it, the likelihood, basically the likelihood term, and the prior odds, which is saying that before conducting any experiments, like our prior belief, how every one of the hypotheses is true against the other one. And in a lot of cases, if you see that, oh, actually they will, for like a more generic study, a lot of cases they will actually set the prior odds to 0, not 0, sorry, prior odds to 1. And therefore, a lot of cases you can see people just keep saying that, oh, what's the base factor? They just don't talk about the odds ratio at all. But if effectively, we should actually use the odds ratio rather than the base factor. The good thing about this kind of hypothesis testing is the Bayesian setting compared to, let's say, frequentist likelihood ratio approach is that actually also include the so-called Occam's razor. So what is Occam's razor saying? In a very simple English, is that if two hypotheses or two models can explain the data equally well, the same data model should be used. So therefore, it's simply saying that, oh, if you have more free parameters, your model should be penalized. Because like you can, if you have 10 data points, if I use a 20 degrees polynomial, of course you can fit it extremely well, but you have 20 degrees with just 10 data points. What's the point of adding all these parameters? But this is a bit hard to actually quantify. But with Bayesian, the good thing is actually it can automatically quantify it for you. So here is a very simple example. So first, let's say there are two different models, two different hypotheses. The first one, hypothesis 1, saying basically is a simplest model you can find with no free parameters. And the likelihood that you get from this hypothesis is just a fixed value, L log. And for H2, now is a hypothesis, a model with one single free parameter. With the likelihood goes of something like L log, but with a Gaussian shape around theta log. So you can look at the maximum likelihood for these two models are the same. So they can explain the data equally well. The likelihood ratio is 1. And for this, because now for H2 we have a free parameter, so you also need to put like a prior for this parameter, and let's say it's just also a Gaussian centered at the same peak theta point, but with let's say a big difference spread, theta, sigma theta. And then now I can go through the whole Bayesian calculation, like calculating the evidence. For H1, it's very simple because it's no integration needs to be done. L1 is already the evidence. And for H2, you need to do one integral, but also it's very simple, just two Gaussian multiply together, you get another Gaussian, and you get something like this. What's interesting is that if you look into the odds ratio, or actually the capital base factor, it will be something like the square root of 1 plus sigma theta squared plus sigma squared. Now there are two things that you should look into here. Or actually, let's look into something. So in case, if you remember, sigma theta is the width of the prior in sigma 2, and in hypothesis 2. So in case our prior approach is data, so basically there's no free parameter. Then sigma theta will become 0, and now this odds ratio becomes, or the base factor itself becomes 1, because now hypothesis 2 is becoming hypothesis 1 again. Of course, they're the same. No free parameters, no penalization, whatever. But if you actually have the sigma theta extend to a very, very large number, then you can see that now in the Bayesian sense, hypothesis 1 is more favored. Not because they fit the data worse or better, just because it has more free parameters and more range for parameters to grow. That's exactly what Occam's razor is talking about. But actually, there's something more. In our case, if we just think about Occam's razor, we'll say that, oh, there are 3 parameters, there are 4 parameters, so it's more penalized and so on. But here, actually also telling you not just the number of free parameters, but also what's the range of parameters that you allow. Like a wider parameters, you will be much more penalized compared to tighter parameters. And how do you define as why, how it's tight? You see, it's this ratio here. It's actually saying that how the spread of the prior compared to the spread landscape of the likelihood function. But of course, there's a problem with the Bayesian hypothesis testing. So first, it cannot be used to calculate the actual probability. You see that when we just calculate the odds ratio, basically it's just the ratio between probabilities. The reason for that is that maybe I should go up. Yeah, the reason for that is actually this quantity here. So it's like given no hypothesis, just the background information I, how likely I can get the data, which is something like unless the hypothesis itself is exhaustive, you cannot calculate it. And also, if you want to, in case you have exhaustive hypothesis, so you can actually calculate it, to actually use the Bayesian evidence to calculate actual probability, now you really couldn't fully trust on the noise model itself or the likelihood function, which we know is not always the case. Like even for gravitational waves, the likelihood itself is actually quite noise motivated, stationary Gaussian, which you can plot the noise and see that they're Gaussian. But still, there are cases that are glitches and so on. So it's at the end of the day, it's just an approximation. So unfortunately, for a very robust hypothesis testing, the frequentist approach is still the way that we would go. And the frequentist approach can go with following lines. So first, you under the null hypothesis, let's say there's no gravitational waves in the data. And then you generate a bunch of testing statistics. For instance, let's say the base vector, you use the testing statistics. And then you have a distribution of the background. And now we have the detection, then you can actually calculate like the p-value of it, or you can also generate another set of testing statistics with an alternative hypothesis. And with these two backgrounds, you can compare, you can see how sensitive your experiment is. Because like if your testing statistic give the same distribution regardless of null or alternative hypothesis, then you should not use this testing statistic. It's not doing anything for you. And then, like I said, if there's actually like a detection or some value, so you can compare with the background, and then you will see, oh, what's the p-value or how likely I'm wrong, basically, the false alarm probability. So a bit more in detail. So like in here, I'm plotting a first schematic distribution of the odds ratio with alternative hypothesis against the null hypothesis, given that the null hypothesis is true. So therefore, this one is the background. And with this distribution, we can actually calculate so-called, let's see which one is which. Yeah, the alpha is the fourth. Beta is the false alarm probability. So let's say we have a detection of an odds ratio of O, and then we want to see how likely actually this value can still be explained by the null hypothesis. And we can calculate the beta. And in case there's a detection, or actually there's evidence of rejecting the null hypothesis, then you expect this black dashed line, I should use this one, the black dashed line to be very, very on the right side. Then therefore, you see a beta is integrating the distribution from the value all the way to infinity, you will see a very low beta. And actually, there's also like, if you want to say there's a 5 sigma detection, you should have a beta around 3 times 10 to the power of -7. But of course, rather than actually calculating everything every time, and then you say, oh, the p-value is not high enough or so on, you can actually pre-calculate the whole thing and say that, oh, actually, I want the threshold for me to claim there is some discovery to be, let's say, 5 sigma, and then I can calculate all the way back for the threshold of the odds ratio. And then from there, you can just compare the value every time. Let's say you did all this calculation, you know that 5 sigma is like odds ratio of 10, then you have a 5 sigma detection, and you just every time you say 9, throw away, 6, throw away, 11, yay, paper, we get a prize or whatever. And also, as I said, you can also like compare like how sensitive your experiment is given a threshold that you want. Let's say for a 5 sigma threshold, again, I calculate the threshold as the previous slide, and that generates a foreground So therefore, it's the distribution of the testing statistic. But now the alternative approach is true. It's under the alternative hypothesis. And then compare these two and see how much of the probability mass of the foreground distribution actually exceeding my threshold. Then I can calculate something called, often refers to the so-called efficiency. So therefore, given this now alternative hypothesis, how many times or how likely I can actually see something that is, I would say, is a discovery. Maybe before I jump into conversion method, is there any questions? Yeah.
So the way you use the equation, it seems like a random variable, right? And
Yeah.
it's a random variable, but in what sense is it actually? Because usually it's just something you compute from your Bayesian model, and it's not really random, right?
Yeah. Yeah. So maybe I should go.
And Peter, can you be sure to repeat?
Oh, yeah, sure. Yeah, so what is asked is that in this Bayesian parameter estimation setting, you see like in the left-hand side, you are treating the theta as a random variable because like the distribution you treat as a random variable. But we know in the actual world, it's not random variable, it's a parameter. So how does it connect the dots and so on? So actually there's a very fundamental difference between differential statistic and Bayesian statistics. Because what Bayesian statistics start off is saying that, oh, I want to have some kind of measurement on plausibility. So how likely something to be true, quantified. But then later they found actually, I think it should be cost. Like later I found that given a set of axioms, you can actually show that the plausibility measurement will follow the same mathematical structure as a probability theory. So you can see in here, actually, in this term, although they are all probability distribution, but they talk about different things. So for the prior itself and the posterior, actually, they talk about the plausibility of these theta to be given by the data and the hypothesis. While the likelihood, a lot of time actually probability, like you're looking to noise model, looking to the background. So actually they can count it or they can actually basically calculate the probability because there's always noise. So data itself is more or less random in some sense. But remember here, the data here are not exactly random variables, although we treat them as such, but actually deep down in the logical sense, they are plausibility, they're not probability. But of course, we can still calculate like credible region and so on, treat them as such, but deep down there. Any other questions?
So,
oh, yeah, sorry.
The randomness of this Bayes ratio stems from the randomness of the data.
Yeah, only the data is random. The data itself is not random, although we treat them as such. Although, yeah.
We have a question on Zoom.
There's a question on Zoom, let me see. I can't see anything. Let's check.
Ah.
Okay, microphone be brought a bit closer to Peter.
Yeah, sure.
Yeah.
You want to unmute and go?
Yes, hi, thank you. In this Bayesian analysis, how do you define the prior? Because I think for different analysis, the prior can be different, right?
Yeah.
How do you define the prior for different analysis, like different transients?
This part is, I would say, more art than science. So, of course, there's a way to, if you want to define a prior, the best way would be so-called like a Jeffrey prior. So basically, you have a prior inversely proportional to the sensitivity of the parameter. Basically, you calculate the Fisher matrix, you flip it. So the region that has lower sensitivity, you give it a higher probability, higher sensitivity, low probability. So you can so-called explore the range better. But in practice, we know it's not feasible because calculating the Fisher matrix itself is not very stable. If you put it in a sample, then your algorithm will die. So sometimes actually it's more like what kind of prior we put in there to one, make sure that actually the prior itself is not like putting too much information into the analysis. So that's why a lot of cases we try to use all those like maximum entropy distribution, like uniform prior, uniform in log prior, Or in some cases, we know there is a bound, maybe you have a log normal, or sometimes you have a normal distribution. But all this is actually very specific to the science case you want to answer, and very specific to the question that you're handling. Because there's no like one prior to rule them all to say that, oh, we should always use that prior. There's no such thing. But then, of course, with Bayesian, the problem is that now your answer is always have some kind of prior footprint in there. But of course, so that's why in our case, we also need to check like how much, if I change the prior in a sensible sense, how much my conclusion will change. That is something that we are also need to check sometime. But yeah, this question itself is, trust me, it's much more difficult than you would think. We have a lot of discussion about this just because of the prior.
Okay, thank you. I have another question.
Yeah.
You mentioned that if the two hypotheses works like almost same, then we need a simpler model, right? Like if they explain the data equally well. So what if the hypothesis doesn't explain the data equally well? Then do we need a complex model, right? So how do we define the complexity of that model? Like how much level of complex do we need for the model?
So this one is, I'll answer in two ways. So first, like this Bayesian, let me see which slides I should have this integral. I will just use this integral. So this integral here, therefore, to calculate the evidence, actually is hold for any hypothesis. You can always calculate this Bayesian evidence. And this Bayesian evidence actually will encode everything. This one is just a very special example that I have the two models have the same peak likelihood, but in practice, of course, it will be different. But then this Bayesian evidence itself actually encodes everything. So first, what's the peak likelihood would be, and what's the spread of it, and how much complexity is in there, and so on and so on. So this Bayesian evidence actually incorporate everything, put it into one single integral. And for the next part of the question, you want to ask, like, how do you measure complexity of a model? What is a red line going around? How do you calculate the complexity of the model? Now that one actually is not that simple. Of course, there's an approximation to calculate, let's say, a so-called Bayesian effective dimension. What it effectively does is to actually put some kind of second order approximation to your likelihood function, and then you can calculate the spread to see what's the degrees of freedom actually in there, in the posterior and so on. Then you can actually have a measurement of an effective number of dimensions, or basically effective complexity in your model. But that thing is also like approximation. So to actually measure the complexity, there's some kind of open question. But remember, this integral here, not just consider the complexity, but also consider the shift in the likelihood and so on. So it's a competition between the likelihood gain and the complexity, additional complexity that you include.
Okay, thank you. Thank you very much.
No more questions? Then we jump into a computational method. This is a bit more complicated, I would say. I really want to remove this red line. So for computational methods. So now with all these like Bayesian framework mathematics set behind, now I want to do some actual calculation. We have a detection, we want to analyze it. What should we do? Or what's the goal they want to achieve? So there are mainly two parts in the Bayesian computation method family. Actually, it's exactly what I just mentioned before. Parameter estimation and hypothesis testing. So for parameter estimation, therefore, we want to look into the posterior distribution. And one of the very common way of doing it actually is generate samples from the posterior distribution. The reason for that is because with the samples, you can actually calculate a lot of the calculation very simply. That you want to have a marginalized distribution, just take a column, plot histogram. We want to calculate the average, sample mean, and calculate median, sample median, a lot easier. In a lot of cases, actually we use the so-called Markov-Chain Monte Carlo, MCMC, for sampling of the posterior distribution. But of course, we also want to calculate the Bayesian evidence, right? As I showed, like, oh, Bayesian evidence is so good, it has outcomes razor, it has everything. But we'll calculate it, and it is very, very hard because it's a high dimensional integration. If you have 10 parameters in your model, it's a 10-dimensional integration. You have 20 parameters, it's 20 dimensions. So not that easy. So there are, I'll talk about two ways to solve this problem. One is the so-called parallel tampering MCMC, which actually would not just calculate the evidence, but also improve the robustness of the MCMC. And the other one is the commonly used, actually we use a lot, is the so-called lesser sampling. Although it starts off to calculating the evidence, but actually it will also give you the posterior samples as a byproduct. So Gaussian Monte Carlo. So the idea of Gaussian Monte Carlo is just evolving your state. So given a iteration t, now we have a distribution of p theta, t and pt of theta, yeah. And I want to have it iterate to the next state, to pt plus 1 of theta. What we do is that for any Markov chain, actually we define a transition probability. Therefore, how it is go from theta to theta prime, and then we can transit this distribution to another state. And in order for this kind of, because you see it's a very generic transition, so how can we get the posterior distribution out of it? So for it to be actually useful, we will need to have some kind of properties that need to satisfy in your algorithm, in your Markov chain design. So first, the design probability, is p bar, therefore is the posterior distribution, has to be invariant under this transitional probability. So basically, you put in your design distribution, you just still get the same distribution out, it should not change. Or more in practice, is more useful in the form of like detail balance. So therefore, given a design distribution from the particular point, let's say theta prime, and jump to theta is equal to a point in theta jumping back into theta prime. So basically, that equilibrium. So one point jump to there, there's one point jumping back to here, so nothing changed. And so also the next part is the ergodicity. So let's say that given any initial distribution, I can't pronounce this word. Ergodicity. Given any initial distribution with enough or like with the iteration tends to infinity, you should always get a design distribution. And one of such algorithm for MCMC that is most commonly used is the so-called Metropolis-Hastings algorithm. But actually, a lot of cases people just using Metropolis, not even the Hastings part. So how does it work? So we actually set up like a bunch of so-called walkers, or let's consider just one walker, so just one point. You're sending in the primary space at theta t, now you're at t iteration. And you want to know where that walk to theta prime. How does it work? So first, in this Metropolis-Hastings algorithm, the first thing they need to define is the proposal distribution or proposal function. So basically saying that given a theta, how likely I will get the theta prime of it and generate a sample of it. So actually that's why our case, we make sure that this distribution is something that is very easy to sample from. Otherwise, you are just shooting yourself in the foot. Yeah, just using a hard distribution to sample a harder distribution. You are not doing anything. So let's say you're in theta and you propose a new point theta prime. Then now, given a new point, should I accept it? Should I actually walk to there? From there, actually, you calculate the so-called acceptance probability given by this form. It's basically the ratio of the design probability with 1 over the ratio of the proposed probability in the reverse direction. Actually, as a fun exercise, I will ask you to try to derive this acceptance probability from detail balance. Actually, it's not that hard. You need to write a few lines, then you should be able to figure it out. And then if I accept it, then of course I will walk to theta prime. But in case I don't accept it, let's say the probability, the posterior probability there is too low, then I just stay where I am, then just stay where you are. And then with enough iteration, like this figure here, you just keep going. Now accept, but this one you reject, you stay in here, accept. Oh, this one is too low, reject, and stay, blah, 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 blah. Then you get your distribution of the side. Or for our case, the posterior distribution. Yeah.
Do you have any kind of step size to remove the local minima?
Yeah. So So you ask whether with the way we can actually get away from local extrema. That's actually a hard question. So actually, because it's all encoded in here in the Q in your proposed distribution. Of course, you can put your proposed distribution extremely wide, so actually jump through everything. But then in that case, you're also jumping all around, but not like centering at the high posterior region. If you use a very tight Q, then now okay, you're very good. You get a good posterior. Now you keep stuck here, but you're stuck. You're not jumping out. So actually, to solve this question, or more precise, the question, let's say there's multimodal with this distribution, while they're connected with low posterior probability region. So how do you jump from there to there? Actually, one way of solving it is the next thing I'm going to talk about, the parallel thinking, which actually solve exactly that question. Yeah, parallel thinking. So, it's a very good question, so I can jump right into it. So, for the NCMC that we see, actually, it's very hard for you to actually handle this kind of multimodal distribution. Like the Q has to be not too wide, not too tight, so it's very hard to make a good Q. And also, this kind of, you can see that we also only get the posterior samples and no evidence estimation. And we know that's something that we actually really want. So what is done, one way to solve it, so-called parallel thinking NCMC, what it does is that now, rather than just sampling the posterior distribution, just one chain, I create like a clone of chains. But each one of them is sampling a bit different posterior distribution. In particular, we introduce this power 1 over T to as a power correction to the likelihood function. And you can see that with T of 1, you just get back your posterior distribution, nothing interesting. But let's say you have a T of 100. Now you can see that your likelihood is basically has less power, while it's mostly something like from the prior, which is like smoother compared to the posterior distribution. So therefore, with higher temperature, you can actually, you're sampling like from a smoother target distribution. So it's less likely for it to be stuck because it's just prime, you just walk around, it's a lot easier. But then, at some point, there's a probability that actually the location between two different temperature chain, they will swap location. So therefore, the high temperature chain can help the temperature 1 chain to actually sort of like teleport to a completely new region of the parameter space. And this diagram to show is quite well. So first, I should use my cursor again. So in here, you see it's a lower temperature. That's why you see that jumping much tighter. While in here, the temperature is much higher. So you can see that they're jumping much further away, much smoother. And you can see that now in this point, there's probability that they swap. So actually they swap location. You see this point actually go to here, while this point should go to here. And it just keep go on and on and on. Then if you look into the temperature 1 chain, then again you get the posterior up.
Also, I think on the ground.
No, it's fine.
I'm just like, if there is this swapping happening around the bay, and if, for example, one of the chains approaching the global minima, global extrema, wouldn't it be also caught by this swap, and instead of approaching the actual solution, it would transport it somewhere else, and it would delay the finding the solution?
Yeah. So when people from outside ask, would it be possible, like because we do this temperature swapping, would it be there's a case like, oh, one of the chains is close to the high posterior probability, we're almost there, we're almost at the peak, but we are gone. The good thing is we actually only swap the location. So therefore, actually the point is still around, but just now in a different temperature, it's not gone. And also if you look into this kind of probability that they swap between them, the temperature also included as a consideration, and also look into the likelihood function itself. So therefore, like, it's less likely for this to happen. If you're very around the peak, you're very high likelihood value, then it's very likely you'll be sticking around. But of course, you're a lower likelihood value, and somehow there's a region where the temperature correction actually will change the probability enough for you to jump to there, then you swap. It's not jump, it's just swap location. But then, other than just the posterior samples that I mentioned, you can actually now calculate the evidence with the so-called thermodynamic integration. I think it's just a abuse of the name, but whatever. So, in the first slide, you see that we are basically defining the same evidence integration, but now we include a factor beta here. So again, beta of 1 is the evidence, but with different beta is completely different objects. And if you actually do a differentiation here, we just analytically write it down, you can see that actually the derivative of this log of this thing will give you the average value of the likelihood with respect to a posterior of temperature 1 over beta. And then with some tricks and so on, you can actually see that, oh, the evidence itself actually can be calculated with an integral. Or in that case, if you have multiple different temperature chains in a uniform beta, therefore uniform over, the temperature is uniform in inverse, uniform over T, yeah. Then you can all this, and you can actually calculate the sample average of this log likelihood across different chains. You integrate it, then you get your evidence. Now I will leave this in. I will not try to jump into detail because you have a copy of my slides. You can look into like what is actually going on here. And actually, this term, why this term is 0? Because this one is just the prior itself, which is normalized. So log of this is log of 1 will give you 0. So before going to nested sampling, so any questions? Because nested sampling will be more complicated. So struggling, ready to run. Okay, nested sampling. So this nested sampling itself, actually, I would say is like a spark of genius algorithm, because it's out of the blue and somehow turn this extremely hard question into a much simpler integration, and then it also give you the posterior samples. But of course, it's not perfect, but still it's very good. So for nested sampling, compared to MCMC, now the main goal is actually to estimate the evidence, while we will get the posterior samples as a byproduct. And remember, I will keep using this notation. The evidence Z is just the integration of the likelihood itself. I'm not sure how much time. I have 1 hour. Maybe I should. Yeah. Hey, Michael, how much time do I still have? Hello.
Yes, I just don't. Yeah, I think we can go till maybe 10:15 or so. And so if you
Okay.
maybe another 25-ish minutes, maybe something like that.
Okay. Yeah, okay. That I can cover this. Yeah. Okay, thanks. So the way that nested sampling works is like, rather than calculating this very high dimensional integral, how about convert it into 1-dimensional integral? So we say that, we don't integrate it with the theta, we integrate it with the x, where x is the prior mass. So basically, the x of lambda is saying that it's calculating how much probability mass of the prior has a likelihood that is has a likelihood that is higher than lambda. That's the prior mass. And then you can see that like for prior mass of 0, then you're enclosing the maximum likelihood point. So therefore, it's like no prior mass, of course. It is nothing, it's just 1 point. If a prior mass of 1, now it's the other way around. You're enclosing everything, like the minimal likelihood in the whole parameter space. But then you would say, it's just a stupid trick. How to calculate this integral, how to calculate the prior mass. It's just put this integral into other place. It's not doing anything. So this, I would say, a spark of genius here. Rather than actually calculating the prior mass, you actually treat it as a random error, and you sample it. So for instance, again, the prior mass you see here, in this functional form, Actually, you can actually show that in case you actually have a bunch of points randomly distributed with respect to the prior, then you will be getting a uniform distribution on X. This is something I'm not showing here, so also leave as an exercise. And then now with this, actually it's a very simple distribution, a uniform distribution. Then the ZTF, so the cumulative distribution function of X would be simply like a linear, just a line from 0 to 1, just go with X. But then this one is still not very useful, right? It's still a very broad distribution, and there's no guarantee that the values I sample from will actually be the prime mass for the actual point, because it's very, very wide distribution. So the other part of genius is that rather than looking at one single point, we actually populate it. So let's say there are k prime mass, and then I'm going to calculate how likely, let's say, another random variable is called chi is higher than all of them. Actually, there's something borrowed from order statistic. If you want to look into more, you can search the keyword order statistic. So how likely is chi is higher than all the x, all the kx that we consider. It's very simple, just chi to the power of k. And then you can also have it differentiated with respect to chi, and then you will get the probability density of it. Now, if we look into this distribution with more and more k, the high value of k, the distribution itself actually would be closer and closer than tighter to 1. While I don't have okay, actually I have it here. I don't have it here. So basically, with higher number of k, the spread or distribution actually will largely increase. It will be tighter and tighter against 1. But of course, in these two equations, I just say that the chi is higher than the chi and also x is bounded by 1. But what if the chi and x actually is bounded by, say, x star, some maximum value of the loop? Then now you can actually transform the distribution to the ratio between chi and x star and call this the t, and you will be following the same distribution here. This one is called the straight gauge ratio. So this is the necessary way. You see a little algorithm here because I think it's already the easiest way, but let's look at the dot first. So here I'm considering the case of k equals to 1, so there's only one single life point. So in the first place, it starts at some value L1. And I say that, okay, I randomly sample from 0 to 1. So I think this L1 is x1, is the x of x1. And now from this point, actually I go from the second point. It's now as a higher likelihood. So okay, it's higher likelihood, so now we're jumping into a higher lower prime mass. And what was the new prime mass? So we actually sample the shrinkage ratio t from the previous distribution, and then multiply with x1 and go to x2. And then go again, do the same procedure from x2 to x3 to x4. So on the prime mass space, what we are seeing is like I'm climbing up with a high likelihood while my prime mass keeps dropping. In the prime space, when I'm just jumping from one value contour to the next value contour. And for this algorithm here, I will not go into details. If you're interested, you can look into it. But basically, like it's the same logic that I just mentioned, but now with k, let's say, k of 1,000 or so on, and how to actually capture so-called dead point and live point and so on. But the idea is the same. So now with all this bunch of, so basically this plot here, with all this bunch of likelihood and the prime mass, you can have the evidence very easily calculated. It's just you can use a Bayesian rule, you can use simple sum and so on, then you can calculate the evidence. But now not just the evidence, because like you see that for each parameter space or parameter point, I have the likelihood, I have the prime mass, therefore I can actually calculate the weight or the posterior weight of all these points. And then therefore I can just resample all these so-called nested samples with this posterior weight, then I can get the posterior distribution. So I think this one I just did on paper is a very good comparison of MCMC and nested sampling. For MCMC, we're always just sampling the posterior distribution. The sample from posterior distribution, we get the posterior distribution. That's it. But for nested sampling, actually we are never sampling the posterior distribution, but rather we're always sampling the likelihood constraint prior. So we need we sample from the prior space where the likelihood has to be higher than a certain value. So that's why for nested sampling, this way you have a hill, you cut it into slice, and you have each one of them sampled, and you put them in the nest, combine them, then you get your evidence, and you get your posterior samples. Of course, sampling is a very big topic. There's no way I can cover it in this lecture today. Like Hamiltonian MC, normalizing flow is also a powerful tool for you to do sampling. And also like nested sampling is also like how actual everything actually approximates is likelihood constraint prior to improve efficiency. And there's also something new called dynamic nested sampling, which allows the number of live points actually vary as a sample, and therefore you can get a good evidence and also a good posterior estimation in the like balance that you want. Basically more flexible.
Hello.
Yeah, I think that's the question. Yeah.
So yeah, for MCMC and nested sampling, I think MCMC would be easier to implement, right? Because
yes
of the less.
It's not that simple. Of course, if you want to implement an MCMC, it'll be easier. But to get a good MCMC, actually, is equally hard as a good nested sampling. It's just different things.
So like for in these two methods, do we like look for where we could apply them like individually, or like do we try both and then see which one works better for our case?
So in practice, not in practice, but in theory, of course, we should try all these algorithms and compare which one is the best and use it. But in most cases, because of the constraint of, let's say, conversional resources and so on, we actually want to go for nested sampling because they also give us the evidence. But even for nested sampling, if you go online, just search Python nested sampling, you will see there are so many samples. So there's also need to.
Yeah, so the computational complexity for nested sampling would be higher for nested sampling, right? Compared to MCMC?
Not necessarily. Because for MCMC, the problem is that now for MCMC is a chain, so everything is connected. And for you to actually get like IID sample, independent and identically distributed sample, you need to do something called thinning. So in case if your proposal distribution set is not good and you have a very high correlation between samples, then you need to thin, like maybe you sample for 10,000 times, but you need to throw out like 90% of them. So it's not necessarily more efficient.
Yeah, okay, got it. Thank you. Thank you very much.
On the same note, just a short question as a continuation of the previous one. So all these methods require you to re-evaluate your model each time you need to, when you have basically a new set of parameters, you need to re-evaluate the model to get the right input and continue the evaluation. Which method do you like? In your opinion, which method requires the least amount of these evaluations? Assume that the model is very computationally expensive, and you prefer to call it as fast as possible. Which one do you choose?
If you are likelihood function, so it's what is asked is that in case the likelihood function itself is very expensive, and I want to minimize the number of likelihood evaluation, whichever should I choose. So if in case the likelihood function is very expensive, at the end, if we want to get a very sensible result, it's very hard to tell which one will use more likelihood iteration. It's very hard to tell. But in case it's very high, I will always go for MCMC because for MCMC, I can get intermediate samples. Actually, it's easier for me to have a warm start, so-called. I can have those walkers sampling in the region that I think is more likely, then I have them walk, so I have to faster for me to get some sensible samples.
And nested sampling doesn't give you this warm start?
No, you have to start from the prior. There are some warm start technique that is available now, but I don't think it's very mature. I personally haven't used it yet. But let's say for necessary sampling itself is all because it's always separate from the prior. So it always has to be distributed as a prior. So that's why as it is and so on.
Okay, thank you.
Now, actually, before I go over this, I also want to mention that's also one of the reasons why there are some cases like you see if the same data being analyzed with the same model but with necessary sampling and NCMC, somehow in NCMC there's really model, but in necessary sampling they're not model. The reason is that sometimes they have used the warm starting, so therefore the NCMC actually does not have a chance to actually see other peak. But for necessary sampling, you're always going from low all the way to high, so it's more likely for you to find those other peaks. So yay, finally the second half of the presentation. No, I'm joking, this one's very short. The NMMA. So like later you will look into a notebook that is on using some kind of use case of NMMA, which is a piece of software as the name, nuclear multi-messenger astronomy. This is exactly doing this, it's doing nuclear study, multi-messenger astronomy, and so on. But what it does, so if you go onto the GitHub page, you will see this summary, a Python library for proving nuclear physics that corresponds to multi-messenger analysis. Not very explanatory. So what it actually does? So for example, like I mentioned, it does all these Bayesian parameter estimation and hypothesis testing. In particular, we use them to look into single or multi-component electromagnetic signal. For single component, let's say the early time signal from the kilonova is a kilonova, or multi-component, so therefore there are some GRB observation that we see there's some residual power, so there could be like a supernova or there's actual kilonova hidden behind. Also, we can also analyze gravitational wave signal in the setting that actually we can input nuclear physics information in there to do some sampling of the US. But of course, the main goal of the show is in the name, is doing multi-messenger effects. So to analyze both electromagnetic and gravitational wave signal all at the same time. But of course, there's also a lot more functionality for you to enable all this. Like there's a functionality to build kilonova surrogate model. And also there's you can actually calculate the prior on the US with some different observation, let's say electric pulsars or lasers. And also by following the interface from UV, we are very flexible in terms of our sampler. You can actually choose whatever sampler you want to use. So one of example is the kilonova 8027 GFO. Like on the right side, all these colored dots are the photometric or the AB magnitude of the different filter, the different band for the 8070 GFO. And this band here is a band split light curve, and then you can see that by actually doing this Bayesian analysis, we can actually get a sense of, okay, the band split light curve actually can explain the data in some sense. But of course, we can also get the post-zero distribution, where you can plot them as a corner plot, where you see the distribution of each parameter and diagonal line. And on all this panel, you will see like a 2D distribution of all these different parameters, and you see correlation. And this title is something that you look into the notebook. But of course, we can also do, as I said, hypothesis testing. So in here, this GRB 211211A is a very interesting event in the sense that we see there are residual powers, and you want to know what it is, what could be explained these residual powers. And because our software is flexible enough, we actually put a bunch of different combination of models like in here, or different GRB structure, and then we can calculate the corresponding base vector with respect to the peak, the most highest model. And then from here is what we use from this analysis to say, oh, well, most likely this event actually is a GRB plus a kilonova. So similar to 17 or 17.
Is I was also I mean I'm part of this probably should know it, but I still like to ask, depending on the actual value of this base factor, how sure you are, like basically from the magnitude of the value, can you tell how certain is the result?
Yeah. So to actually go from base vector to how certain, the most robust way would be the 4-point background approach that I mentioned.
Yeah.
But of course, it's very expensive. And also, it's very hard to do in some sense because you need to have some kind of background distribution. You need to know some kind of population information for to do that. But of course, we don't have it yet, so there's no way to do it. But rather, actually, there's some cases you can actually use the so-called Jeffrey interpretation, basically saying that if the base vector is higher than certain value, then you should put certain sense of confidence in it. But that one is more like a rule of thumb. So therefore, it's less robust than the background problem approach. But when it's not available to do it, that one would be the best case. So you go from there and you can see. So basically, so like for this base vector here, I would say there's no preference. The preference for different kilonewton model is very weak, based on what is basically nothing. But you see here, then you can say that, okay, then supernova may not be very, cohorts or supernova may not be very likely because you see base vector of 10 is much higher now. But then also we can do multi-messenger analysis with propagational waves, kilonova, and GRB. So in here you see that this left-hand side of the color plot actually is something that took us a lot of time and a lot of computational resources to do it, which is something that is basically we can do all the analysis all at once, and we can observe all the correlation between all these parameters. And that is not something that was able to do before NMMA. But then if we want to go something rather than just astrophysics. So actually this kind of multi-messenger analysis also enables us to actually look into nuclear physics, but with different aspects. So like we can look into nuclear physics in the astrophysical side, we can look into the nuclear physics from the heavy ion collision side to compare all them and combine them. So this is like a more general multi-messenger, not just messenger from the sky, also messenger from the Earth. So this is the end of my talk, and so want to do some cool science. This would be something that is exciting, and I hope everyone will enjoy and try to learn, get the skill, and just do some fun science. Yeah, thank you. Oh, perfect time.
We're gonna clap for you, Peter. Clap, 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 clap. Thanks, Peter. You covered a lot of stuff in an hour and 10 minutes. Do we have questions? About to hit a coffee break, you know, and then cruise break. Anything anyone want to touch on? All right. Well, at least there's nothing here. Anything on Zoom, folks? We had a handful of questions during the thing. Yeah, there's a number of questions about you know, sort of further details, further content. I'll have the TAs point you to some lecture materials from the data science class I run. I'm sure Peter probably has some sort of source materials he might also share, and then we can share. In terms of slides, yeah, we're going to post the slides on the summer school website, kind of at hopefully sooner than the YouTube channel. So yeah, we'll have the slides up, just maybe not immediately.
How can NMMA be used for neutron star in EOS? Yeah, so for the first two questions, I think Michael has answered it. So for the last one is that actually we also have a functionality to actually just generate a set of neutron star equation of state. And then of course, with all this equation of state, we can actually put it into this necessary sampling or Bayesian analysis, then we can get posterior on the neutron star equation of state. So therefore, we can look into the neutron star equation of state with this NMMA. So silence.
And the notebook doesn't quite hit the equation of state constraint stuff, but we do point to the documents or the documentation which goes through a worked example of how to do EOS constraints. So we can take a look. All right, folks, I think I'm going to call it here because we're running a little behind. So I think we'll take a break till 10:45. So we'll give folks a full 30 minutes to, you know, do the coffee answer the emails and so on, and we'll resume then. So see you all in 30.